Okay, so this video is going to be the second in a series in which we're trying to make the simplest version of a physics engine that we can using Python 3 and Turtle Graphics. So this physics engine is also going to include basic animation. And that's where we left off the last time. So just to sort of recap, uh, what we're trying to do here is create something like this to model some physical properties in nature, and in this case it's a very small subset. All we're modeling is velocity and position. So each circle has a velocity, and the velocity dictates the next position between each frame. And then there's one other special effect here that we have where each one of these circles will collide with the wall, right? So when it collides, basically we switch the direction of the velocity. So if it collides with the top wall, that's velocity in the y direction. We negate that and make we keep the same magnitude of the velocity, but then we just make it negative, and so it'll be coming down. Then when one of the circles hits the bottom barrier, right, then we will negate that, so it will go from a negative value to a positive value and start going up. Right? And we'll get into this a little bit more. We're going to talk about vectors a little bit. Okay, so this is sort of the goal. And last time we left off, we had part 1. And so this is sort of where we started or ended up, and we got animation working, right? We did some basic setup. We've got a black background. We've got a canvas size, and we set up our main animation loop. Okay, so this is the part 1 code. I'm just going to recap this real quick. We imported our libraries. We set our color mode so that way we can generate random colors at some point. We set up the tracer. So actually this turns off the tracer. And the tracer is just the animation of the turtle actually drawing the things. Okay, so we're not interested in that. That's useful to learn about how the computer draws these things, but we're not interested in that. So we're turning that off, and the benefit of that is we get to draw things much faster. If you do turn the tracer off, then you have to manually call turtle.update whenever you want the things that you've drawn, like don.goto, any rectangles, circles, whatever you've drawn. If you actually want that to show up on the canvas, then you call turtle.update. And so it's a much quicker render. They call that rendering. Okay, so those first 2 lines we talked about setting up constant variables. It sounds like an oxymoron, but it's not. Constant variables are variables that you set up in your program, and you only ever set them once at the beginning of the program, and you never modify them. So they are constant, even though they are technically, syntactically variables. All right, so we have a width and a height of our screen, and then these were kind of some helper constants that we're going to use here shortly. We have a minimum x value, so in terms of our screen, that's the minimum x here. So with our current numbers, it's going to be negative 320. So the whole width is 640, so half of that is 320, and it's negative. And then positive 320 over here. Same with the y value, the minimum and maximum y. Then we got the screen, and this is all just basic Turtle Graphics setup, right? So we get the screen singleton, we adjust the screen size, which is the actual canvas size, and then we set up the window size, and we added a little bit of padding there so we don't get the scroll bars. Right? Then we create our turtle. Again, we're not interested in seeing the turtle actually draw these things. We've done that in other videos, and so we don't want to see the turtle draw the thing, so we're going to hide the turtle. We also have the tracer off. And then we start in with some helper functions. So one of these helper functions we have is draw a rectangle, and we give it an x, a y, width and height, and color, and we use this function basically to draw our background. Okay, so we specify the center of our rectangle, and then the width and height of the screen is going to be the width and height of the rectangle that we want, and we specify the color. Right, so color is passed in to draw a background as a parameter, and then we pass it in as an argument when we call draw a rectangle. Okay. So then this time.sleep is something you don't necessarily have to have in your code. This is specifically because when I run this program, I have a dual monitor set up, and so when I run this, part 1, it starts, the window opens on my other monitor, so I have to drag it over. So that just gives me a chance to drag it over before it starts executing the animation. Okay, so this is optional here. I don't want to change that. All right, then we get to the good stuff. We get to the animation loop. All right, so here we have an X and Y value, and this is associated with our one circle. Now eventually we're going to have lots of circles, so we're going to have to find a way to keep track of an X and Y position for every single circle, right? And then here, what we did was each time through this loop, we added 1 to the X value. So now keep in mind the X and Y values are basically pixel coordinates, right? So if we look at this, every single pixel has a coordinate. When we specify the width, that's 640 and the height is 480, and that's pixels. So a pixel is the tiniest dot on the screen that can represent any color. All right, so here what we're doing is we're changing the position, right, by a certain number of pixels each time. Now we mentioned that there were problems with this last time, right? One of the problems is this is totally dependent on how fast the machine you're currently running this on is operating, right? This while loop is going to execute as fast as the machine will possibly let it, and there's lots of factors for that. There's hardware. If you have a faster processor, this is going to run faster, but also other things running on your machine taking up compute cycles that would reduce the speed of this, right? And we don't want that. We want a consistent look and feel, right? So in this, for example, no matter what system I run that on, the speed of all those circles is the same. Okay, and in order to achieve that, we need to, instead of just updating the X and Y position by a certain number of pixels, we need to bring time into the equation. Okay, so each time through the loop, we need to specify how much time has passed since the last iteration of this loop. Okay, so this while loop, this is the animation loop, and each time through this while loop we are generating 1 frame of our animation. So it's one complete drawing, one complete rendering of our animation, right? And then the user sees that, right? And then we go back and calculate a new frame. Okay, so you may have heard something in high quality video or video games about the term frame rate. So this right here is going to have a very high frame rate. Right? We're not spending a whole lot of time building stuff. We have 1 circle to draw, so we can execute this loop pretty quickly. The frame rate has to do with how often you can execute 1 single frame. So 1 cycle through the animation loop would be 1 frame, and the rate of that is how many frames can you make per minute or per second. So usually, like depending on what you're doing, it used to be 30 frames per second. Now 60 frames per second is high quality, like video game quality frame rates, right? So for what we're doing, and again, Turtle Graphics is not designed to really be something that you would make a physics engine with. We're just using it because it's fun to learn about. So it's not nearly as efficient as some other libraries that you might use to make games or something like that. So it's not as performant, but we know how to use it. It's pretty simple, so we can use it to start understanding physics engines. Okay, so what do we need to change here in this while loop to make it so that we reference time between each individual execution of the animation loop, so each individual frame. All right, so we haven't modified this file yet since last time, so it's a good idea to duplicate a file when you have something working, and that way you can always come back to it. There's lots of, you might play around with something and then forget how you had it, and a cat might walk on your screen or on your keyboard or something like that. Any number of things can happen, so it's a good idea to periodically just make a copy and then you've got a backup from where you were last. All right. So here on part 2, let's take a look at how we're going to first deal with this idea of frame to frame getting a time. Right. So if I want to know how much time has passed, I'm gonna open Python 3 here in interactive mode, and I can import the time library, which we already have imported in our file. But if I call time, which is the package, and then it has a function in that package called time, I call that function. This is the number of seconds since January 1st, 1970. Okay, and that has to do with back then data was scarce, and so they chose sort of an arbitrary point in time to use as the baseline for these functions. But lots of programming languages have something like this. This is the number of seconds since 1970, January 1st, 1970. So in JavaScript, it's actually milliseconds, right? So we can verify this. We could say time.time. And if we were to divide by 60, there's 60 seconds in a minute, so that would give us minutes. And if we divide that by 60, there's 60 minutes in an hour, right? And then if we divide by 24, there's 24 hours in a day. And then we could divide by 365. And we see it's right now we're currently at in December of 2020. So this is 1970 plus 50 is 2020, and then towards the end we're at the tail end here. Okay, so this is just proving that this actually is seconds. All right, now that's going to be useful when we talk about our animation. We have to have some concept of speed, and more than speed. Like speed is how fast you're moving, but we're going to be talking about velocity. Now, what's the difference between speed and velocity? All right, so actually I need to grab a file real quick. So speed is, we all know what speed is, it's how fast you're moving, but velocity is speed, but there's an extra bit of information. There is the concept of direction as well. So it's how fast you're moving with a particular direction, and this becomes very useful for our animations. Okay, so let me grab this real quick. All right, I'll move it to the desktop. There we go. All right. So, oh, not the SVG. I want the PNG. All right. We'll just do it like this. All right. Sorry about that. So here, this is the idea of a vector. Okay, so it has, we have velocity, so it has a magnitude. So this is 5 meters per second. So this is our vector, and we can componentize vectors. Okay, so here this is the x direction, and here this is the y direction. Okay, so this is really nice because that's how our graphical systems are working. We're using two-dimensional graphics, and there's an x and a y coordinate. So it's really nice that vectors have this this ability to be componentized into an x portion. So if we have this speed, we can break that up into two vector components. So this is 5 meters per second in this particular direction. We can break that up into the x component, right, which is a smaller magnitude, 3 meters per second, and then a y component, right? So this is the y velocity, and this would be 4 meters per second. And so with the Pythagorean theorem, you can calculate if you have the x magnitude and the y magnitude, you can calculate the resultant magnitude. So Pythagorean theorem is a squared plus b squared equals c squared. So that's right here. If you have 3 squared plus 4 squared plus 5 squared, that's 9 plus 16 is 25. Okay, but the key takeaway here is with vectors, you can componentize a vector in any direction to an x portion and then a y portion. So that's going to be very useful. All right, so knowing that, the way we can keep track of an object's direction and their speed and direction is just by keeping track of two vectors, the velocity in the x direction and the velocity in the y direction. Okay, so to do that, we would just add a couple of extra variables here. So we'd say velocity in the x direction, and we can put something in here, and we have to start thinking about units a little bit too, because we're gonna make this in terms of time, right? So this is going to be something like commonly meters per second, and something you'd use a lot in physics, meters per second, right? So we have to decide how many pixels a meter is, right? But we could say, all right, so this would technically be pixels per second, right? So we would say, let's say we want our ball to move relatively slowly. We want it to move, I don't know, 30 pixels per second. All right, so again, this is Vx, velocity in the x direction. So here we're going to have Vy, which is velocity in the y direction. And this could be anything as well. We might say that this is positive 50, something like that. All right, and so basically the way this works is we have to calculate how much time passed since the last iteration of the loop, right? We went through and we talked about time. Okay, so this is where this comes in. So we're going to have a value. This is the last time. So each time through this loop, we're going to calculate the current time. We're going to call that now, right? And we also have to keep track of the last time we got the time, right? So the last now, we're going to start that off, initialize that variable at time. Okay, so again, this is just going to be the number of seconds from 1970, right? And so in the loop, what we have to do in order to update the positions, we have to get the current time. Now equals time. Okay, now here we have to compare these two values. Now the first time there should be a little bit of change, not very much at all, right? Because the computer's not doing much between this line of code and then this while loop, right? So all of the time is taken by drawing all of the items, right? That's what takes up compute time. That's what takes up processor cycles. Okay, so really it's from one loop iteration to the next that it's really going to start having a certain time delta here. So what I mean by time delta, that's just the time change, right? So that's the time interval that we're talking about. What has changed? We have, let's see, what do we want to call this thing? It's the interval, right? It's how much time has transpired since the last iteration of this loop. Okay, so the interval is going to be the difference between the current now and then the last now, right? So if you think about it, the current now should always be bigger, right? Because time always progresses forward. So there's always more seconds since 1970, right? So that's the bigger number. We're going to say now minus the last time we calculated now. All right. So that is the interval. That's the amount of time that's passed since we last called or calculated the now variable, right? Okay. So how is this useful? Well, we see this interval now is going to be in seconds, right? So if we know how many seconds have passed, we can multiply the seconds by our velocities. So the x velocity is 30 pixels per second. So if this interval was 1 second, then that means I would want to add 30 to my x value. Realistically, these intervals are going to be much, much smaller because our frame rate is going to be really high. But whatever the interval is, we multiply by the number of pixels per second. So let's say it takes a half of a second to iterate through this loop one time. It's actually going to be much faster, but just for the sake of argument. So the interval would be 0.5 seconds. So that means if this thing is moving 30 pixels per second, in half a second, it should be moving 15. We multiply by the velocity in the x direction by the interval. But then there's also a component of velocity in the y direction. So we would have to multiply the velocity in the y direction by the interval, and that's how much we would increase y here. All right, so let's do this. Let's say x, instead of just adding 1 pixel here, we're going to be using the velocities, and we're going to say x equals vx times the interval. Okay, so this is going to be added to whatever position is already there at x. And if the velocity was negative, it would be subtracting, right? Because we're adding a negative, right? And so we do the same thing over here. The velocity in the y direction times our interval. Right? And then this is pixels per second. All right, so let's see how this looks. This is part 2. Okay, so that's moving pretty quick. So if we think about 30 and 50 pixels, so this is 320, so that's like 30, and then 50, oh, that should be a plus equals. Okay, so in the y direction, I'm adding the velocity, right? Each iteration through, I'm adding the interval times the velocity. So previously, I just had minus to show that it goes down. But all right, so what we're really doing here is you could use the Pythagorean theorem to calculate the resultant vector, right? So that would be 30 squared plus 500 squared, and take the square root of that, right? And we see we can slow this down. How many pixels per second do we want? Let's try, let's go really slow. Let's try 5 and 5. Close that. All right. So we see that this is moving. We have x and y position. We have pixels. Now, to illustrate that this is actually doing what we think it's doing, what we can do is we can artificially add a sleep in here, time.sleep, and this is going to show us, this is going to simulate if we had a whole lot of things to render. That would basically slow down the construction of each frame, and so it's going to reduce our frame rate, but the object should still move just as fast, right? It's not going to, it might be a little bit more jerky because you'll have fewer frames in the animation, but the speed of it will actually be the same. So time.sleep will simulate this with maybe a 0.2 second delay. So that's time.sleep. It basically just pauses the program for 0.2 seconds and then comes back. All right, so that went slower. That was not what's supposed to happen. So we have an issue here somewhere. So let's investigate that. Let's reduce. I just reduced the delay. So theoretically, this should go faster, which again was the whole point of this. So there's something going on that we need to take a look at. All right, and then if we did 0.01 for the delay, see, that's about right. So notice it was going the same speed, but this last one is smoother. Right? You see it's smoother as it moves. Let's change the size of the circle so we can maybe see this a little bit better. and we'll change the starting point also. Let's make the starting point negative 200 and then negative 200. All right, so this is the initial x and y value of our circle. These are the velocities of our circle. All right, so this should be going 5 pixels per second, and it's going much faster than that. So we do have an issue there. It looks to be accelerating too. So what do I have here? So this is number of pixels per second. This is pixels. So my interval, let's examine the interval. It's time.time. So now minus the last now is going to be the interval. So the new x value, 2x and y. Let's see, does anything here modify x and y? So this might be an issue of reusing variables. I'm going to call this circle x and circle y. Circle vx, circle vy. All right, so you have circle x is going to equal whatever it did before plus circle velocity of x times the interval. And then we have circle y, circle vy times the interval. Okay, then we go to our circle x, circle y. All right, and we draw our circle, turtle.update, time. And so just so we get an idea of what this interval should be, we're going to print out the interval, and we can kind of debug this. So that this is a good opportunity to just go through debugging. This happens all the time when you're coding. You have some issue, it's not doing logically what you think it should, so you've got some error in your code somewhere. So pull that over. Okay, so yes, we do have an issue here. All right, so this makes sense. So our interval is going 10, 11, 12. So our interval is getting bigger and bigger and bigger. That shouldn't happen. It's not taking 16 seconds or 17 seconds between each cycle here, right? So I know what the issue is here. We can cancel that. Basically, we never set last now again. So the first time we set this variable, last now, is at the very beginning of the while loop, right? And so now we calculate at the beginning of the loop, but what I forgot to do was I have to set last now again to now at the bottom of the loop. So think of it this way: as we progress through this while loop, this takes time to execute all this code. Then we get down to the bottom and we say last now, which we can do this before or after the sleep, it doesn't matter. Last now equals now. Okay, so we're updating this variable. This variable is supposed to be the last value of now that we had from the last time through the loop. All right, so now is calculated as time.time. Now initially we set this to time.time just so we have an initial value, because otherwise I can't subtract the current value from nothing, right? I have to have a value there. So I get time.time. Time progresses just a very small amount, and then we get a new variable now. So this first interval is going to be extremely tiny. So now is a little bit bigger than last now, right? We print out that interval. And as we go down through, we draw everything, but then we have to save the time now that we stored here. And the reason is because we have to make this calculation the next time through the loop. This is supposed to be the new interval. So now I'm going to keep this print statement in there, and you're going to see the difference when we run this. So that's about right. So each frame, and see, this is moving much, much slower, right? And if you think about it, 5 pixels is about that amount. So it's like 1 Mississippi and move 5 pixels, right? So, and here we see how much time is executing. or how much time is elapsing between each frame, right? So there is, about 0.1, 0.2 seconds, right, between each frame. Okay, so a 0.01, right? So that's a lot. So that's, if it was 0.01, that would be 100 frames per second. If it was 0.02, that would be like 50 frames per second, right? So that's pretty good. So this is pretty good resolution, pretty good frame rate type of drawing. But notice how steady it is now. And the only difference, that was one tiny little bit of code that we forgot, that was last now equals now, right? And that makes each interval the smallest amount of time that's passed since the very last iteration through the loop. All right. So that's a good example of how to debug minor issues that pop up. Oops. So I'm gonna delete this print statement now, and we can go back here and we can close this. All right. So we have this concept of animation. We have the x value, the y value, velocity x, velocity y, and we are updating those values, right? Now, the next thing that we want to do is we're going to have to add multiple items. We need multiple circles in our display, right? So I think I'm going to save that for next time, and we'll just pause right here. So the main thing we learned about this time is vectors, and we learned about keeping track of an x and y position, and we know that if you have a vector, it can be componentized into the x direction and the y direction. And we saw when we actually ran this, part 2, we see that those two things are combined, right? We're going over 5 pixels and then up 5 pixels for each second. Over 5, up 5, right? And we can speed up the velocity here and take a look at what that would look like, if we wanted to go 15 pixels in the x direction. Well, what's that going to mean? Well, if we're going 15 pixels to the right and only 5 up, the slope of that line is going to be shallower, right? So we can see this. So previously we were coming up at a steeper angle like this. Now we're at a much shallower angle, right? That's because we're going, each second we're going 15 pixels and then up 5. 15, 5, 15, 5, right? Okay, so that's the concept of componentizing the velocities, right? Now the next phases of this, we're gonna do a little code cleanup. So drawing the actors. Right now we just have one actor, okay? And we're keeping track of that actor with variables here. And these are in the global scope, which is probably not necessarily a great idea. If we're going to have hundreds of these circles, right, we need to keep track of a circle array, right? We need an array of these objects. Each one of our circles has to have these properties. So it's going to need an x value, a y value, a velocity in the x direction, and a velocity in the y direction. So what we're going to have to do is we're going to have to kind of make a dictionary collection of these values that's going to represent each one of these circles. If you're more advanced, you'd probably want to use a Python class for this. That's more ideal, but I want to keep this accessible to beginners who may not know about classes. So we're just going to reference these items in a dictionary. All right, so we're going to do that next time. We'll look through the code again, see if we made any changes up here. No, that's good. Yeah, it was mainly this stuff that we changed. And then down at the bottom, this time.sleep, it's nice to keep that there so you can test out the frame rates, but you technically don't need it. However, you'll get the maximum frame rate if you don't have this time.sleep. However, it will spike out one of your computer processors. So it's sometimes good to at least put a really small sleep down at the bottom. You'll still get pretty good frame rates. All right, so we had the last .now down there at the bottom. All right, so that's enough for this video. We'll see you next time.